Hi everyone, I'm Jinhan Kim from KAIST, and I'll be presenting the reducing DNN labeling cost using Surprise Adequacy, an industrial case study for autonomous driving. This work is done with Jeongil from Hyundai Motors and Robert from Chalmers University and my advisor Shin. So there are many considerations when we adopt machine learning models into the industry, such as collecting the label, tuning the hyperparameters, and we also have to think about the training costs and resources. Especially for supervised machine learning, one of the key challenges for real-world application is a large number of data with labels. Such labels are very important because they are used as a ground truth during the training the model. But the problem in here is that the humans are inevitably involved to label the data. So in this work, we focus on reducing the human labeling costs in the industry. If we think more about the human labeling, the human is placed back in the cycle to help training, testing, and retraining the machine learning models. The image shows that an example cycle of human labeling, which is an oracle to guide retraining the model with more data points. So we call this kinds of setting the active learning. In this active learning setting, we can select some new data points to be labeled because we posit that only some portion of the data set will be helpful and the less of the new data set will not be helpful because they are similar to the existing training data points. So as a result, it only increases the retraining and labeling costs without increasing model performance. So we have a new question: how to select or how to prioritize new inputs to be labeled by human for efficient labeling and effective training. In this work, we target the image segmentation problem with our industrial partner Hyundai Motors. Image on the right show an example of segmented image with several classes, such as human, car, or road. The image segmentation is essential step in the pipeline of autonomous driving system. From the camera on the car, images are captured and machine learning models segment them into separate objects, which are processed to be alerting danger situation as well as it is used to planning of steering or some actions. Data labeling for image segmentation is known to be costly because humans need to label each pixels in the image. And in our case, images are from video frame, which results in a large number of images to be labeled. As shown in the screenshot, the Google Cloud provides the labeling costs of several tasks. So in the dataset we study, each image typically contains 5 to 10 segments. So if we require at least 3 individual workers per image for the robustness, and if we assume the standard 24 fps video, the only 1 second of the video results in costing roughly between 300 and 600 USD. Okay, here's a real example from Hyundai dataset. The left image is captured from the camera on the data collecting car. So you can see the load and white load markers and 2 black objects on the left and on the right, which is our vehicles. This is the right image is a human labeled image, which is segmented into several objects with different colors. So for example, you can find the vehicles are colored in red and the load is colored in blue. So let's get back to the original question: how to select or how to prioritize new inputs to be labeled by human for effective and efficient training. Let's assume that we have 6 new images to label. For human, it is hard to know what is the good inputs to be labeled first to improve the model performance. We posit that the inputs which are not same as training inputs is going to be effective because they are not seen in the training phase, which means that it is easier to be misclassified. This kind of similarity between training input and a new input can be easily computed pixel by pixel distance, but this kind of direct computation cannot reflect how the model process the input. So, which means we do not know inside of the model. So in this work, we use surprise adequacy to effectively capture the distance using internal state of the neural network. Let me briefly introduce what is the surprise adequacy. The surprise adequacy is proposed to find good test inputs, which should be sufficiently different from training inputs, but not much different from them. So it basically quantifies how different a new input is to the training data set. So let's get back to the original example. The surprise adequacy can be computed for each input like that. The high SA value means it can be misclassified easier than other inputs. So representing good inputs to be labeled first. Let me introduce more about surprise adequacy. The one important notation of surprise adequacy is called activation trace, which captures internal state of the neural network. So it is kind of proxy of internal logic of the neural network. So in this example, the activation trace is a vector with 0.1 and 0.3 and 0.5. Our first adequacy metric is called likelihood-based surprise adequacy, LSA. It uses the prior distribution of training data in order to quantify how much the new data is surprising to the network. So we collect activation traces from training data and we do corner density estimation to quantify its novelty. And the second surprise adequacy is called Mahalanobis distance-based surprise adequacy, MDSA. Unlike the LSA, the MDSA is direct distance metric between distribution and a point. So in our case, the distribution is going to be distribution of training activation traces, and the point is going to be activation trace of the new input. So MDSA is known to be more efficient than LSA because it only uses the mean and covariance metric of the training activation traces. Unfortunately, we are not able to show the full model used by Hyundai models, so we only show the deepest layers of the semantic segmentation model trained by Hyundai models. The size of the input and output image is W by H, and we extract activation trace right before 1x1 convolution layer, which has W0 by H0 by D dimensions. The problem in here is that the size of the activation trace is not fit into the size of input and output images, which makes it hard to use this activation trace as a classification of each pixel in the original input and output image. So to handle this problem, we reuse upsampling layer in the model. The activation trace is upsampled and each size is going to be same as the image size. So we can now utilize this pixel level activation trace to find surprising pixels in the image. Collecting these activation traces of the training set, we can now calculate LSA or MDSA, which means we can identify which image is worth to label first. Here we use two different datasets with about 16,000 and 60,000 training images and about 2,000 and 10,000 test images. This dataset has in total 14 segmentation classes, for example, lanes and load markers. The void represent external load structures or unknown object, which means that it can be relatively noisy because void class does not have any features. The standard evaluation metric of image segmentation is intersectionable union, which is called IOU. So IOU is ratio between the intersection area and the union of two segments. When the predicted segment is exactly the same shape as the labeled segment, the IOU becomes 1. The less they overlap, the closer to 0 the IOU becomes. In practice and also in our study, IOU is computed per class to identify the classes that are not predicted well. This is an overall pipeline of our analysis. The left side of the figure shows the pre-processing phase, which is done offline, and the right side shows how we compute surprise adequacy when we have new input. Each pixels of the image has its own SA value, so we average them with their predicted class to identify which class label is not confidently predicted. Our first question is sanity check of activation trace and surprise adequacy. We expect that the model perform worse with more surprising input. So which means that we expect when SA value is high, IOU is going to be low and vice versa. Let's see the result. We sort test images with their IOU values and we plot SA and IOU relationship figures. For each input image in the test set, one green and one black circles are plotted. The green represents the IOU for a class or class group in the image, whereas the black represents SA value. We can observe the negative correlation in the load class, but in case of void class, there is no clear correlation. When we compute LSA, the similar patterns are found. The void class still shows noisy result, but the load class show negative correlation. The areas labeled as void lack consistent features, so noisy results are expected, as no meaningful segmentation is possible based on their own features. So from the correlation analysis between SA and IOU, we concluded that SA is successfully applicable to semantic segmentation. Once the SA analysis is completed for a new test input, multiple views becomes available for the image. The original input image, the result of segmentation, and an image whose pixel values are the SA values of the input image. If the manual labeling is available, we can also place the label image and the difference between the model segmentation and the manual labeling. Combining them, we generate a live video visualization of SA analysis. Let's see. In the top, you can see the original input, ground truth, which is human labeling, and inference the image by the model. In the bottom row, you can see the difference between ground truth and the model inference, and MDSA thresholding, which highlights some pixels with high MDSA values, and lastly, the MDSA heat map. We expect that MDSA is similar to the difference of ground truth and inference. The next question concerns how much labeling cost can be saved by using SA values as a guidance. So before labeling, there is no ground truth, meaning that we don't know the IOU value of the image. Basically, we want to know image with low IOU to label them earlier than others. For example, we can make it as a binary classification problem. If we know the IOU values and set IOU threshold as 0.4, then we can find some images whose IOU values are below 0.4 like this. So we say these images are problematic and other images are not problematic. The choice of the IOU threshold was made based on the experience from the engineers at the company. However, we do not know about IOU values, so we compute surprise adequacy for each input to find the relationship between the problematic image and SA value. In this study, we assume that we do not label some portion of images with the lowest SA values, meaning that we skip labeling images which are not surprising, but that causes some loss of accuracy because even if it is not surprising to the model might have misclassified the image, meaning that low IOU value. Here's a result figure of the study. The x-axis means that we do not label X% of the images by selecting them starting from the lowest MDSA values. And the y-axis represents the classification inaccuracy. By not labeling these images, we are effectively accepting the model segmentation as a ground truth. For example, let's see the green upside down triangle at 55% and 0.05. The data point suggests that even when we skip labeling 55% of the low SAE inputs, only 5% of the skipped images will be actually below the IOU threshold of 0.5. Based on the study, we can say that SAE can be successfully used to reduce the cost of the manual labeling. And that's it for the presentation. If you want to see the full experimental literature, please refer to our paper. Thanks.